Good day, everyone. I am the one who are going to present to you for today, and we are the group 3, and I am the one who are in task of this video and the discussion of our PowerPoint presentation. Okay, we are going to start. We are discussing the surface irrigation. Surface irrigation is the application of water by gravity flow to the surface of the field. There are 3 types of surface irrigation: the furrow, border, and basin. The furrow consists of furrows and ridges. The border is a strip of lands with a downward slope but are as horizontal as possible in cross-section. The basin is a horizontal area of land surrounded by earthen bands and totally flooded during irrigation. Next is the criteria for the selection of the surface irrigation method. In selection depends mainly on soil type, crops to be irrigated, the irrigation depth, land slope, field shape, labor availability, water source. First one is the soil type. In 3 surface irrigation methods, we prefer the heavy soil than a light soil because heavy soil has the lower infiltration rate, while the light soil it has high infiltration rate that is favor deep percolation losses, resulting to low field application efficiency. Next is the type of crops. In furrow irrigation, we use this irrigation method in maize and vegetables, and this is suitable for irrigation row crops. And furrow are also suitable for shallow rooted crops. The border shape irrigation can also be used for row crops or for close growing crops that do not favor water ponding for long duration, such as wheat and alfalfa. Any crop, whether row or close growing, that can stand a very wet soil for up to 24 hours is best grown in basin. Here is the example of furrow irrigation. As you can see, we have the ridges and the furrow, where the furrow is where the water goes, and the ridges is where the plant will be planted. This is the example of border shape irrigation. It consists of ditch, gates, and separated by bands. Next is the required depth of irrigation application. In here, if we are going to use small depth, we have to use the furrow irrigation method. If we are going to use a large application of water, we're going to use the basin irrigation method. Of the 3 surface irrigation method, basin irrigation can have higher irrigation efficiency and use less water for the same crop on the same soil than the other methods, as water is confined within bands. Land slope. All surface irrigation method favors flat land, as steep slopes would necessitate excessive land leveling in order to avoid erosion. In land slope, we are preferably using flat lands for the surface irrigation to avoid soil erosion. Flat land with a slope of 0.1 is best suited for basin irrigation since basin irrigation is requires minimum land leveling, and basically this irrigation method has zero slope. The border irrigation can be steeper, and even up to 5% of slope can be considered in border irrigation. But in furrow irrigation, steep slope is not suitable in this method because of the small channel, which could result in erosion. Next is the field shape. For all three types, regularly shaped field are preferable. Labor availability. Basin irrigation requires less labor than the other two methods. And this is, are we saying that basin is more preferable if the site is critical in labor, there are labor shortage. We are recommending the basin irrigation. These are some tables. We're not going to discuss this anymore. These are the soil types for bordership. And in here, the basin area in square meter for different stream sizes and soil types. In stream size, there are different stream sizes, and these are the areas that are going to required in basin area. If we have the sand, soil, sandy loam, clay loam, and clay. Selection of an irrigation method based on soil type. So we have the soil type here, and every soil type there are surface irrigation method that are going to use. This is the components of the surface irrigation. So in here we have the water source, and if we go in here, this is the partial film that will narrow the irrigation. And in here we have the first drop to increase its velocity, and this is the division box that are going to our ditch in here before it cross the gate pipes that is right below the ditch, and this is are going to distribute the water in the field. Okay, the next one is the surface irrigation design steps. These are some we are going to discuss. And in step 1, collecting basic resource data at farm. The data includes a topographical map and showing the proposed irrigated area, the farm and field boundaries of water source or sources, PowerPoints such as electrical lines in relation to the water source and area to be irrigated, roads and other relevant general features such as obstacles, data on water resource, quantity and quality over time, on water rights and on cost of water where applicable, the climate of the area and its influence on the water requirements, the soil characteristics, the type of crop intended to be grown in their compatibility with both the climate in the area. So in step 1, we are basically collecting basic data in the farm. And in step 2, we are going to analyze the data that were gathered in step 1 to determine the parameters in the design parameters. These are the peak and total irrigation water requirement, infiltration rate of the soil to be irrigated, maximum net depth of water application per irrigation, irrigation frequency and cycle, gross depth of water application, preliminary system capacity. In step 3, we are going to decide which surface irrigation method we're going to use. In step 4, the system layout. 5, land leveling. This is where the labor begins. 6, the determination of water reticulation plan. If we are going to use the continuous supply of water, we are going to rotational or on demand. The 7th step, canal design. So we're going to design the canal. Tertiary canal sizing, secondary canal sizing, main canal sizing, canals cross sections. Step 8, drainage system canal sizing. Step 9, identification and design of hydraulic structures. We're going to identify and design hydraulic structures. Steps 10 to 12, canal longitudinal profile, the main, secondary, and tertiary. 11, production of bill of quantities. In step 11, we're going to produce the bills that we are going to use. The bill of the canal, structures, and list of other materials that we are going to use in building some requirements or offices, buildings, fences, etc. Step 12, production of system operation is instructions. This is where the whole system are going to build. Next is the soil assessment, the 4 phases of irrigation. The first one is the advanced phase. This is where the water begins from the upstream to the downstream until it reaches the storage, which is the second phase, the storage or ponding phase. This is where we are going to stock some water for our field. And next is the depletion phase. This is the time between the stop of the inflow at the head end and the appearance of first bare soil that was underwater. In depletion phase, this is the phase that the water is going to evaporate or percolate on the soil until we see the first soil that is submerged in the water. The last phase is the recession phase. This is the time when the water starts to disappear at the head end until it eventually resides from the whole field. So in here, recession phase, this is the time where the water is going to infiltrate the soil. The contact or intake opportunity time in hour or minute that any particular point in the field is contact with water. This is the graph where the phases are located. Next is contact time. Depth of infiltration varies in relation of contact time. Contact time can be increased by using flatter slope. The contact time is going to increase if the slope of the field is flatter, because the water can be retained in it and it will not go down if it is flatter. And the contact time will be decreases if the slope of the field is steepening, or the stream flow is increases. Infiltration. Infiltration or intake rate is the rate of which water enters the soil and is expressed in millimeter per hour. It is critical to surface irrigation at is determine the following. The time of soil should be in contact with water, the rate at which water should be applied to the field. In infiltration, where we are actually studying it and how our soil can hold the water. Water infiltrates rapidly when soil is dry, but then later slows down until it reaches a steady state, referred to as a basic infiltration rate. When the basic infiltration rate reaches the cumulative infiltration curve becomes a straight line, and the basic infiltration rate curve become a horizontal line. And this is the diagram. As you can see, the infiltration rate, as the time increases, the infiltration rate goes down because the infiltration will occur. The water begins to infiltrate the water as time goes by, and as we discussed, if the infiltration rate becomes the basic infiltration rate of the curve, it's going to be flat and it reaches the cumulative infiltration. As you can see, the cumulative infiltration curve is increasing, and if the basic infiltration rate becomes flat or increases, the cumulative information curve is going to straight up. Okay, this is the typical infiltration rate for different soils. Soil type, we have the sand, sandy loam, silty loam, clay loam, and clay. The infiltration rate in sand is greater than 30. Sandy loam, we have the 30 to 20. Silty loam, we have 10 to 20. Clay loam, we have 5 to 10. And clay, we have less than 5 millimeter per hour of infiltration rate. We all know that in soil texture, heavy soil or the clay has a smaller pores, and light soil has the highest infiltration rate because of larger pore sizes. The infiltration rate is a difficult parameter to define accurately, but it has to be determined in order to describe the hydraulics of the surface irrigation event. When planning a furrow irrigation scheme, one can determine the infiltration rate by two methods: the infiltrometer method or actual furrow method in furrow irrigation if furrow irrigation is to be used. Design parameters for the infield work. These are the crop water requirement, DNAT, irrigation efficiencies, DGROS, irrigation frequency, irrigation cycle, and system capacity. The parameters are determined more in the same way as for sprinkler irrigation. System capacity refers to the discharge that has to be abstracted from the headwork during a given period per day, and it is used for the design of headwork and the conveyance system. It is determined by the following equation. We have the Q is equals to volume over time, where Q is equal to discharge. We have the unit of cubic meter per hour or liter per second. And V is equals to volume of water to be abstracted per day. And T is equals to irrigation duration per day, where the volume of water to be abstracted per day is obtained as follows. The equation is V is equals to 10 multiplied by A multiplied by D cross, where V is equals to volume of water abstracted per day, which is unit of cubic meter, and area. A is equals to area irrigated daily, measured in hectares. The D gross is equal to the gross depth of application at overall scheme level, and the 10 is equals to the conversion factor to convert mm to cubic meter per hectare. Next is the area irrigated per day and system capacity. The area irrigated per day can be calculated as follows. Area is equals to AT over IC. A is equals to area irrigated per day. AT is equals to the total area. IC is equals to irrigation cycle or days. This is the summary of the calculated design parameters for surface irrigation scheme. This is the design parameters and the symbols. The net depth of water application has a symbol of DNet. Calculated irrigation frequency of IF, same as the adjusted irrigation frequency. Adjusted net depth of water application is same as the DNet. Adjusted allowable depletion is equals to P. Proposed irrigation cycle is IC. Gross depth of water application, D gross, same as the gross depth of water application in field level. Area to be irrigated per day is equals to A. Volume of water to be abstracted per day, assuming an irrigation duration of 10 hours per day, is equals to V. System capacity is Q. System capacity for 24 hours conveyance and night storage is equals to Q. Here, as you can see, is the layout of the surface irrigation scheme. This is the contour lines or topographical sketch. As you can see, there are contour lines, roads, canals, and drains. Next is the guidelines for producing surface irrigation layout. First is the water conveyance. Water is conveyed from source to highest point in field, either by gravity or by pumping, depending on the elevation differences between water source and highest point in field. Pipelines can be used where there is enough head difference to overcome frictional losses in pipes or when pumping, and usually take the shortest distance to field. Infield layout. Layout is determined by the following factors: the topography, farm size and degree of mechanization, possible length of furrows, border strip, and basin. Farm size, this is the farm size and degree of mechanization. This is where the machineries that we're going to use in land leveling. On flat land with slope of less than 0.4%, field canals run along contours, while secondary canals run at right angles to the contours. Furrows are often constructed perpendicular to the contours. Next is the guidelines for land with a gentle steep topography. Secondary canals are constructed on the top edge of field following the contour but slightly running away from it to maintain a gradient for water flow. Field canals are then constructed in such manner that they cross elevation contour at almost right angles. Canals are often constructed at a grade of 1:500 and gentler slope for unlined canals. Furrows are often pegged around 1:300, but it can deviate either side depending on the desired contract time. Next is the land leveling. Proper land leveling is important for efficient surface irrigation. It involves moving of soil in order to have level fields for basin irrigation or uniform sloping field for furrow or border strip irrigation. Besides being expensive, too much soil movement tends to leave shallow topsoil in areas of cut, which is not ideal for crop production. In land leveling, this is important in our field because having a leveled land will determine the infiltration of our soil. A detailed topographic survey, preferably grid, is needed to calculate the most economic land leveling requirements. Based on the spot height of the grid and the required gradient of the land, the cut and fill can be calculated. The three most widely used methods for calculating the amount of soil cuts and fills are profile method, control method, and plane or centroid method. There are some land leveling use of computers. A number of programmers have been written to calculate the land leveling requirement by computer. One such program, written by E.C. Olsen of Utah State University, is called Level 4 EMX. It calculated land grading requirements based on the least square analysis for both rectangular and irregularly shaped fields. Next is the importance of land leveling. It is to enable efficient irrigation, removal of surface water. Low areas may receive excess water or waterlogging. High areas may not receive sufficient water or low yields. Salt, as in borders, may accumulate in high areas. In the previous slide, we determined the three ways in determination of water reticulation plan. First is the continuous water delivery. Each field, canal, or pipeline receives its calculation share of total water supply as an uninterrupted flow. Water is always available, although it may not always be necessary to use it. The method is rarely used in small irrigation scheme. Next is the rotational water delivery. Water is moved from one field canal or pipeline or from a group of field canals or pipelines to the next. Each user will receive a fixed volume of water at defined interval of time. This is quite common method of water delivery. And the last one is the water delivery on demand. The required quantity of water is delivered to the field when requested by the user. This on-demand method requires complex irrigation infrastructure and organization, especially when it has to be applied to small farmer-operated scheme where the number of irrigators is large and plot holding are small. Next, we have the design of canals and pipelines. Design of pipelines. In pipelines, pipe surface irrigation system, water is transported in enclosed conduits or pipes. The pipes can be all buried with outlet in the form of hydrants protruding above ground level on field pipes, or only the conveyance and supply lines can be buried, with field pipes being portable and laid above ground. In latter case, the above ground pipes are made by aluminum fitted with adjustable gate openings. Pipe system for surface irrigation, unlike pipe system for sprinkle irrigation, do not require a lot of heads at the hydrant outlet. The situation where the head is not adequate, small power pumps would be used with low operational cost. If the water level at the headwork is higher than the water level required at skim level, the water can be transported through pipes by gravity. These are some methods commonly used to introduce water into the field. First is the secondary ditch, and there are some tube called the portable siphon. This is where the water travels into the field. Next is we have the main ditch and the secondary ditch, and in here we have a pipe that connects the two ditches, and from the secondary ditch we have smaller openings that will transport the water through our field. And in letter C we have this pipe with several orifices or gates that having scale and slide gates. These scale are used to regulate the water that will be flowing in the field. And this one is, I think it's pipe or hydrants from the ground, pipes buried, and next is the design of pipelines. If the water level of the headwork is lower than the water level required at skim level, then the water needs to be pumped through the pipe to arrive at the skim at a required elevation necessary to be able to irrigate by gravity from the field inlet onwards. For calculation of friction losses, just as in a sprinkler design, manufacturer friction loss chart or equation like the Hazen-Williams can be used. The Hazen-Williams equation is given. Hazen-Williams HF100 is equals to K multiplied to the quantity of Q over C raised to the power of 1.852 over the D raised to the power of 4.87, where HF100 is equals to the friction losses over a 100-meter distance. K is the constant, 1.22 times 10 raised to 12 for metric units, and Q is equals to the flow, liters per second, or this is maybe the distance, the discharge, and C is equals to the coefficient of retardation based on type of pipe material. C is equals to 140 for plastic. D is equals to the inside diameter of the pipe. Next is the C value of different materials and some example we're going to solve. Material is PVC. We have the constant of 140 to 150. Asbestos cement of 140. Cast iron 130. Galvanized steel 120. When aging, the roughness of cast iron and galvanized steel pipes increases. For example, for a year-old cast iron pipe, the C might be reduced to 120 and to 100 for 20 years in cast iron pipe. These are example problem. Assuming that a 50 mm inside diameter and 20 meter long hose is used, the friction losses for a flow of 1.6 liters per second will be as follow. The equation is equals to HF100 is equals to 1.22 times 10 raised to 12 multiplied to the quantity of 1.6 over 140 raised to the power of 1.852 over 50 raised to the power of 4.87 is equals to 1.64 meters per 100 meter of friction. For the 20 meter hose of head losses, our head loss will be HL is equals to 1.64 multiplied the 20 meter over 100 meter is equals to 0.32 meters. We have the total of 0.32 meters for the head losses. Design of canals. The canal dimension and longitudinal slope, whether for irrigation or drainage, can be calculated through trial and error with the Manning formula. This formula is derived from a continuity equation and the equation of unsteady flow. These equations have been simplified by assuming steady uniform flow in the canal. The continuity equation is expressed as Q is equals to A multiplied by V, where Q is equals to discharge, having a unit of cubic meter per second. A is equals to weighted cross-sectional area, having a unit of square meter. And V is equals to water velocity, having a unit of meter per second. The Manning formula can be expressed as Q is equals to Km multiplied by A sub S multiplied by R raised to the power of 2/3 multiplied by S raised to the power of 1/2, or Q is equals to 1 all over N multiplied by A multiplied by R raised to 2 over 2/3 multiplied by S raised to 1/2. where Q is equals to discharge, Km is equals to the Manning roughness coefficient, N is equals to the roughness coefficient, and A is equals to the wetted cross-sectional area, P is the wetted perimeter, R is equals to the hydraulic radius, S is equal to the canal gradient or longitudinal shape of the canal. Flowchart for canal design calculation. This is the chart on how we calculate a canal design. Okay, in here it shows the different canal parameters. As you can see, in here we have the freeboard, we have the flow, the roughness, and this is the wetted cross section. This is the wetted perimeter. This is the wetted perimeter, and this length is the water depth, and this is the length of the bed width, and this is the slope. Next, AS and P and thus R is the Manning. In the Manning formula can be expressed as D, B, and X, where D is equals to water depth, B is equals to bed width, X is equals to side slope or equals to horizontal divided by vertical. For a trapezoidal canal, AS is the sum of a rectangle and two triangles. The Manning formula is applicable to uniform flow. The amount of water passing every section is the same, means velocity is constant. Calculation of the cross-section perimeter and hydraulic radius of a canal. AS, or the cross-sectional area, is the sum of rectangle and two identical triangle at the edge and is expressed as AS is equals to B multiplied by D multiplied by X D squared is equals to D multiplied by B plus XD. P, or the wetted perimeter, is sum of bed width plus the two side slope from the canal bottom plus to the top of water level. This is calculated from a formula of C squared is equals to A squared plus B squared and expressed as perimeter is equals to B plus 2 multiplied by D squared plus DX raised to 2, the quantity raises to 1/2 is equals to B plus 2D multiplied to the quantity of 1 plus X squared raised to 1/2. Hydraulic radius R is expressed as R is equals to AS over P is equals to D over D multiplied the quantity of B plus XD all over B plus 2D multiplied to the quantity of 1 plus X squared raised to 1/2. When the computed discharge is equal to the required discharge, the velocity needs to be checked to ensure that it is acceptable. With high velocities, flow becomes supercritical and become difficult to siphon. The state of flow is checked using the Furrow number Fr, which is given by the formula Fr is equals to V all over the quantity of G multiplied by L raised to 1/2, where V is equals to the water velocity, G is equals to the gravitational acceleration, and I is equals to the L hydraulic depth of an open canal, defined as the weighted cross-sectional area divided by the width of the free water surface. Fr is equals to 1 for critical flow, Fr greater than 1 equals supercritical, Fr less than 1 for subcritical flow. It is important to maintain the Froude number of 1 or less so that the flow is at or below the critical level. Factors affecting canal discharge. The canal gradient. A canal with steeper gradient but with a same cross-sectional discharges more water than a canal with a smaller gradient. Canal roughness influences the amount of water that passes through a canal. A higher roughness, the higher the ability of the canal to transport water. Hence, the smaller the required cross-sectional area for a given discharge. Canal shape. Canals with narrower beds and higher water depth have a smaller wetted perimeter and thus a higher discharge than canals with larger beds and lower water depth for a same cross-sectional area. This is due to the fact that the hydraulic radius increases if the wetted perimeter decreases, while keeping the wetted cross-sectional area the same. Side slope. For unlined canals, soil texture determines the side slope. Next is the maximum water velocity. The higher the velocity, the higher the discharge. For unlined canals, ensure that velocity is non-erosive as well as self-cleaning. Next is the freeboard. Freeboard stands with F. It is vertical distance between the top of the canal bank and the water surface at design discharge. It gives safely against canal overtopping because of waves in canals or accidental raising of water level, which can be result a closed gate. The safe freeboard can be calculated from the following equation. Equation is F is equals to C multiplied by H raised to 1/2, where C is equals to 0.8 for discharge of up to 0.5 cubic meter per second or 1.35 for discharges in excess of 80 cubic meter per second, and H is equals to the water depth. For line canals, F range from 0.4 meters for discharges less than 0.5 cubic meter per second up to 1.20 meters for discharges of 50 cubic meter per second or more. For very small line canals with discharges of less than 0.5 cubic meter per second, the freeboard depth could be reduced to between 0.5 to 0.3 meters. Next is the canal shape. Although the trapezoidal canal shape is very common, other canal shapes including V shapes, U shape, semicircular shape, and rectangular shape canal can also be designed as shown in the figure. This one, you can see the arrowhead. This is the V-shape canal, and this is the semicircular shape canal, and this is the rectangular shape canal. Next, this is the type of surface of a pipe or canal that can be used in our irrigation, and this is the range of roughness in every material that are we going to use. Typical canal side slope. These are the soil types, and every soil type there are corresponding side slope that we are going to use in constructing a irrigation canal. Maximum water velocity ranges for earthen canal on different types of soil. In soil type, we have the sand, sandy loam, clayish loam, clay, gravel, and rock. In sand, we have a maximum velocity of 0.3 to 0.7 meters per second, and so on. The recommended bed width over water depth ratio earthen trapezoidal canal. We have the water depth of small, medium, and large, and the BD ratio of 1 clay is to 2 sand, 2 clay is to 3 sand, and greater than 3. The bed width should be wide enough to allow easy cleaning. The bed width of 0.2 to 0.25 meter is considered to be the minimum, as this still allows the cleaning of the canal with small tools such as a shovel. Lined trapezoidal canal could have similar BD ratio as given in the opposite table. Hydraulic parameters for different canal shape and examples. The first one is the square type or rectangular type shape of canal. We have a water depth of 0.5 meters and a bed width of 1 meter. The area is equals to 0.5 multiplied by 1 is equals to 0.5 cubic square meter rather. Perimeter is equals to 2 multiplied by 0.5 plus 1.0 is equals to 2.0 meters. The radius is equals to 0.5 over 20 is equals to 0.25 meters. The next one is the rectangular shape. We have the depth of 0.25 and the bed width of 2. The area is 0.25 multiplied by 2 is equals to 0.5 cubic square meter. Perimeter is 2 multiplied by 0.25 plus 2.0 is equals to 2.5 meter. The radius is 0.5 over 2.5 is equals to 0.2 meters for the radius, and so on. This is a shorter bed width trapezoidal, and this is the larger bed width of trapezoidal shape canal. Next, we have an example. What is the water depth for a trapezoidal canal with the following known parameters? Q is equals to 0.09 cubic meter per second. We have an S is equals to 0.001 or slope of 0.1%. B is equals to D. Roughness coefficient is equals to 55 with an X of 1 or 45 degrees. V is equals to less than 0.75 meters per second. The cross-sectional area of the trapezoidal canal is given by the equation area is equals to D multiplied the quantity of B plus XD. Substituting the above given data for B, D, and X gives area is equals to D multiplied by D plus D is equals to 2D squared. The wetted perimeter is given by the equation of P is equals to B plus 2D multiplied to the quantity of 1 plus x squared raised to 1 half. Substitute again the above given data for B, D, and X. P is equals to D plus 2D multiplied by 1 plus 1 squared over, raised to 1 half is equals to D plus 2D multiplied by 1.414 is equals to D plus 2.83D is equals to 3.83D. The hydraulic radius is given by the equation R is equals to area over perimeter is equals to 2D squared over 3.83D is equals to 0.52D. The Manning formula is given by equation Q is equals to Km plus AS multiplied by R raised to 2 over 3 multiplied by S raised to 1 half. This gives 0.09 is equals to 55 multiplied to 2D squared multiplied by the quantity of 0.52D raised to 2/3 multiplied by 0.001 raised to 1 half, and we got a 110D squared multiplied the quantity of 0.52D raised to 2/3 multiplied by 0.0316 is equals to 1.807D raised to 2.66, and D is equals to 2.66 root of 0.09 over 1.807, and we have the result of D is equals to 0.30 meters. With an area, we can calculate for the area with 2D squared. Substitute the D is equals to 2 multiplied by 0.30 squared is equals to 0.18 meters squared. We have the velocity Q over A 0.09 over 0.18 is equals to 0.5 meters per second. This means that the water velocity is less than the maximum allowable velocity given of 0.75 meters per second, which is acceptable. However, the Furrow number should be calculated using equation 19 to make sure the flow is subcritical. Fr is equals to the velocity over the G multiplied by L raised to 1 half, where L is equals to area over width of free water surface is equals to AS over B plus 2D is equals to 0.18 over 0.30 plus 3 multiplied by 0.30 is equals to 0.20. Thus, as Fr is equals to 0.50 over 9.81 multiplied by 0.20 raised to 1 half is equals to 0.36, which is less than 1. This means that the flow is subcritical. Seepage losses in earthen canals. Farmers preferred unlined earthen canals because they can be built cheaply and easily and maintained with farm equipment. Unlined canals are also flexible, as it is easy to change their layout to increase their capacity or even to eliminate and rebuild them the next season. However, unlined canals have many disadvantages that make them less desirable compared to lined canals. or underground pipes. They usually lose more water due to seepage, leakage, and spillage. Rodents can cause leakage. The next one is the frequently cleaning is needed because of weed growth. Next is the earth ditches can erode and minder, creating problems in maintaining straight or proper alignments. And labor costs of maintenance of unlined canals are normally higher than of lined canals and pipelines. They provide an ideal environment of the vector and bilharzia. In unlined canals, we all know that this is an earthen canal. This is commonly unformed or can be formed. It doesn't have a uniform shape, or it can be easily made, can be eliminated and rebuilt. So we are talking about the earthen canal made of soil. So we are expecting that seepage, leakage, and spillage will be occur in this canal. Next, when designing earthen canals, it is important to ensure that the slope is such that the bed does not erode and that the water flow at a self-cleaning velocity. So if we are designing earth canals, we must ensure that the slope will allow our canal to be self-cleaned due to velocity of the water. The higher the seepage losses in the canal, the lower the distribution system efficiencies, since much less water than that diverted at the headwork reaches the field. So if we have a higher seepage losses, therefore the water can be reduced, and for that the distribution system will not be efficient or lower than efficient because of the losses of water. Seepage losses and earthen canals. Seepage is difficult to predict. Two simple ways to estimate seepage losses are: number one, measurement of inflow into the outflow from the canal to selected points. The difference between the inflow and the outflow measurement will not only represent seepage losses, but evaporation losses as well. So in here, as we all know, the intake and the output can be the same, but due to seepage, the intake water will reduce and the output water can be lower than the input water. Therefore, it is represent the seepage losses and also the evaporation losses as well. The second one, measurement of the rate of fall of the water level in a canal stretch that has been closed and where the water is ponding. From these losses, the estimated evaporation should be subtracted to get the seepage loss. Usually, seepage losses are expressed in cubic meter of water per square meter of the wetted surface area of a canal section per day. If a field test cannot be carried out, seepage can be estimated from table below, which gives average seepage losses for different type of soil. Seepage could be localized where a portion of highly permeable material has been included in the bank, or where compaction has been inadequate during canal construction. So in seepage, we all see it on not thoroughly compacted soils in the construction of canal, and maybe in highly permeable materials that has been included in the bank. Seepage losses for different soil types of soil, and we have the seepage with a cubic meter of water per square meter wetted surface area per day. We have the impervious clay loam that has a seepage of 0.07 to 0.1. Clay loam and silty loam has 0.15 to 0.23. Sandy loam 0.30 to 0.45. Sandy soil 0.45 to 0.55. Sandy soil with gravel 0.55 to 0.75. Previous gravelly soil 0.75 to 0.90. These are a representation of seepage in different soil types. Next is the canal lining. Canal lining is generally done in order to reduce seepage losses and thus increase the irrigation efficiency. It also substantially reduces drainage problem and canal maintenance as well as water ponding, thus reducing the occurrence of vector-borne diseases. Also, smooth surface lining reduce friction losses, thereby increasing the carrying capacity of the canal. In building a canal lining, we have used these different materials. We have the clay, polyethylene plastics. Example of this is the PVCs, concrete, sand cement, bricks, and asbestos cement. The selection of lining method depends mainly on the availability of materials, the availability of equipment, the cost and availability of labor for construction. Next, here's an example for a canal lining. An earthen canal with a 1:1000 gradient constructed in and using sandy loam is designed to convey 78.3 liters per second for 24 hours per day over a distance of L of 2 kilometers. The manning coefficient of the canal is equals to Km is 30. The side slope X is 1.5 and the BD is 1.5. What is the seepage losses as the percentage of the daily discharge? In the solution, the canal cross-sectional area is calculated by the Manning formula as follows, where Q is equals to Km multiplied by AS multiplied by R raised to 2/3 and S is raised to 1/2, where AS is equals to 1.5 D squared plus 1.5 D squared is equals to 3 D squared, which is the perimeter is equals to 5.10 D. Substitution of AS and P in the equation gives 0.0783 is equals to 30 multiplied by 3D squared multiplied by the quantity of 3D squared over 5.10 D raised to 2/3 multiplied by 0.001 raised to 1/2. We have the D is equals to 0.30 meters. Therefore, AS is equals to 0.27 meters squared and perimeter is equals to 1.53 meters. The total wetted surface area over the 2 kilometer stretch is wetted surface area is equals to perimeter multiplied the length. is equals to 1.53 meters multiplied by 2,000 meters is equals to 3,060 meters squared. The seepage loss through a sandy loam is estimated at 0.40 cubic meter per square meter per day. Thus, the total estimated seepage loss for the canal is total seepage loss per day is equals to 3,060 multiplied by 0.40 is equals to 1,224 cubic meter per day. The total volume of water supplied per day is equals to 0.0783 multiplied by 24 multiplied by 60 multiplied by 60 is equals to 6,765 cubic meter. This means that approximately 1,224 over 6,765 multiplied by 100 is equals to 18% of the supplied water is lost to seepage. Hydraulic design of canal networks using the chart of Manning formula. The hydraulic design of canal networks for irrigation and drainage requires the following steps. Step 1. Design water surface level in relation to natural ground slope and required head for irrigation and fields or for drainage to outlet, taking into account head losses for turnouts and other structures. Step 2. Calculate corresponding hydraulic gradients. Step 3. Divide network into sections of uniform slope and discharge. Step 4. Determine required design, the maximum preferably, discharge per section. Step 5. Select roughness coefficient in side slope, preferred minimum velocity and permissible maximum velocity, the bottom width or water depth ratio. Step 6. Calculate hydraulic section dimensions and corresponding velocity using nomograph series. If available, the nomograph presented in the Manning formula, basic equation and calculator. Step 7. Check calculated velocities against preferred and maximum velocities values. If it is too high, reduce hydraulic gradients and corresponding bottom slope. The gain in head should preferably be used in upstream and downstream canals sections, but if this is impossible, it must be absorbed by drop structures. The chart represented in figure can be used to determine the optimum canal parameters for trapezoidal canals section through trial and error. This is the chart of Manning formula for trapezoidal canal cross section. As you can see, I don't really understand this, but you will see that this is the chart for Manning formula in trapezoidal canal. Next is this is a sample problem. What is the bed width of a trapezoidal canal with a side slope angle of 60% and a water depth of 0.3 meters, assuming friction is equals to 55 and that the canal has a discharge of 78.30 liters per second at a gradient of 0.001 and 0.002 respectively. In order to calculate x, one has to determine the tangent as follows. Tangent 60 degrees is equals to 1 all over x. Therefore, x is equals to 1 all over tangent 60. is equals to 1 all over 1.673. And we have the x is equals to 0.58. Substituting the value of x and the water depth, d is equals to 0.30 meters, and equations 16 and 17 respectively gives as is equals to 0.30 multiplied the quantity of b plus 0.58 multiplied by 0.3 is equals to 0.30 multiplied the quantity of b plus 0.174 is equals to 0.3b plus 0.05, and the perimeter is equals to b plus 2d multiplied by 1 plus x squared raised to 1/2 is equals to b plus 2 multiplied by 0.30 multiplied to 1 plus 0.58 squared raised to 1/2, and b plus 0.6 multiplied by 1.156 is equals to b plus 0.69. The hydraulic radius using equation 18 is r is equals to area all over perimeter. We have the equation of 0.30b plus 0.05 all over b plus 0.69. Substituting the data in the Manning formula gives q is equals to 55 multiplied the quantity of 0.30b plus 0.05 multiplied the quantity of 0.30b plus 0.05 all over b plus 0.69 raised to 2/3 multiplied by 0.001 raised to 1/2. Substituting value of bed width in the formula by trial and error will result in a bed width that suits the design discharge, fixed at 0.0783. Try B is equals to 0.2 meters. The result of the calculation is a flow Q equals to 0.049 cubic meter per second. When the gradient is 0.001, this means that the canal with a bed width of B is equals to 0.2 meters and a water depth of 0.30 meters will not be able to discharge the design flow of 0.0783 cubic meter per second. After a few runs of trial and error, we get Q is equals to 0.0783 cubic meter per second when B is equals to 0.35 meters for the 0.001 gradient and 0.24 meter for 0.002 gradient, with water velocity of 0.50 meter per second and 0.64 meter per second respectively. The engineer in Zimbabwe designed the canal would simply use table 21 to choose a canal section with 250 millimeter bed width and a gradient of 1:500 and 350 or 375 millimeter bed width at a gradient of 1:1000. Calculate the fraud number according to equation 19 gives the value of 0.26, implying that the flow is subcritical. Okay, we are going to watch a video that I added in our presentation. This is an example of surface irrigation. We call the Furrow Irrigation system. Okay, we are going to watch and enjoy.
So the third type of irrigation system we use at the farm is furrow irrigation, that we use a gated pipe to put the water into the furrows. These gated pipes are 6 inches in diameter, and they can be 20 feet long, 30 feet long, and every 30 inches along the gated pipe there's a gate, an opening that lets the water out, and you can open and close and adjust the size of the opening for the amount of water that you want to put into the furrow. Each one of those gates can put out about, depending on how open they are, they can put out as much as 16 gallons a minute out of each gate. We usually have a gate every 60 inches, so we're going to put out 64 gallons a minute onto our field to do basically 3 beds. This farm has been leveled to grade. There's a laser level machine that comes out and perfectly makes your field have maybe a 1% grade, so the water flows downhill. That's an important concept in furrow irrigation, but you don't want it to flow downhill very fast. So I'm going to open this up. And the gated pipe is going to start to fill up. So now we have water coming out of each of the gates, and it's headed down the furrow. And I've shoveled dirt on the back side of the pipe, so the water for sure is only going to flow in one direction, which is downhill. And the water will flow to the end of the row, and then I'll turn the volume down and let it percolate across into the beds. This whole process, depending on the length of the field and what kind of soil you have, could take several hours to get to the end and irrigate the whole field. It is less precise, clearly, because there's more water at the beginning of the field. More water is going to work its way down into the soil at this end of the field, but hopefully you get it down to the end pretty quickly, and then you get a more even distribution of water. So you might think that this system would grow more weeds, but it turns out that because it's only putting water in the furrow, the weeds are only going to grow in the furrow, and it's fairly easy with the tractor cultivation system to cultivate the furrows. So often with this system, it's actually easier to control weeds with this system than it is with the sprinkler system, which is putting water all over the place. So one of the reasons we're not putting water down the middle furrow is that the middle furrow is softer than the outside furrows. The outside furrows are where we have driven the tractor, and so it's been compacted. And what that means is that the water doesn't penetrate down, straight down into the furrow. It's actually forced to go off to the sides. When you run water down the center furrow, the water penetrates right into the furrow, and it can take a very long time to get to the end of the bed because the water penetrates so much better where you haven't driven the tractor. The system uses a lot of water, and it puts a lot of water deep, so it's important to only use really on crops that are deep rooted and can take advantage of the fact that you're putting a lot of water into the ground. And with those kinds of crops, you don't have to irrigate very often. If with the drip system we were irrigating every day or every other day, and with the sprinkler system, with those direct seeded crops, if we were irrigating every day, with this furrow system, you might only irrigate every 10 days or every 2 weeks, depending on the soil type and the weather at the time, how much evapotranspiration there is. This is an ancient system. It functions pretty well. It uses a lot of water. And so in times of drought, it isn't something that people are inclined to use. But there's a certain charm to this, of water running down a furrow.
Okay, this is the next is our simple irrigation system that we produce in a short time period. This is also as the same as on the video, the surface irrigation system used in the video. We have here the you can see, this blue is our pipe, and this is the area of our field having a 650 meters long and 350 meters wide of furrow irrigation. So you can see these gray lines are some of the ridges, and in between these are the furrows. And in our pipes there are some gates, regulated gates that will open in time of irrigation. So that's it. This presentation is prepared by the Group 3 consisting of J.R. Dangil and Jemer S.R. Move, the yours truly, and Jesusa Flores, Meliton Junio Jr., and Jomar Lagunero. Thank you so much for the listening. Thank you so much for listening, and thank you so much for the patiently waiting for a long discussion. And I am deeply sorry for some of the parts of our presentation that you can hear some unnecessary noises. So thank you so much and have a good day. Thank you everyone for this wonderful day. On behalf of my group mates, I, Jemer S.R. Mube, are going to end this presentation